Hello, everyone, and welcome back to the tutorial sessions. This is track one, and we are in our final talk of the day, which is an exciting one. ASTRA-sim and Chakra, enabling software, hardware, co-design exploration for distributed machine learning platforms. So let me introduce our speakers. We have Dr. Tushar Krishna. He's an associate professor in the School of Engineering and Computer Engineering at Georgia Tech. He's currently also a visiting associate professor at the Department of Electrical Engineering and Computer Science at MIT. He has a PhD in electrical engineering and computer science from MIT, an MSc in electrical engineering from Princeton University, and a BTech in electrical engineering from the India Institute of Technology, Delhi. Before joining Georgia Tech in 2015, Dr. Krishna spent a year as a researcher at the VSAT group at Intel, Massachusetts. Wow, I didn't know that. I'm very close to that. Dr. Krishna's research spans computer architecture, interconnection networks, network on chip, and AI/ML accelerator systems with a focus on optimizing data movement in modern computing platforms. His research is funded via multiple awards from NSF, DARPA, IARPA, SRC, the Department of Energy, Intel, Google, Meta, Facebook, Qualcomm, and TSMC. We also have William Wan, who's a PhD student in the College of Computing at Georgia Tech. His research interests include training and inference of distributed machine learning, simulation of distributed machine learning workloads, collective communication optimizations, and machine learning algorithms. So with that, I think we can get started. Just a quick reminder that we are fielding questions in Slack, and we have put the link to that channel in chat, I believe. If not, we will soon. And as those questions come in, we will hand them off to the speakers. So with that, welcome, Dr. Krishna, and please take it away.
Thank you so much, Eve, for the wonderful introduction. Let me just go ahead and start sharing my screen. All right. Is my screen visible?
Yes, looks great.
Okay, perfect. So again, thank you for the wonderful introduction, and I'm very excited to kick off the ASTRA-sim and Chakra tutorial here at Hot Interconnects. I'll just again, they've already introduced the two of us. So I'm a faculty member at Georgia Tech, and my senior PhD student William will actually be running the tutorial. But of course, this infrastructure and framework has actually had several contributors from Georgia Tech and industry, and some of whom are listed here. And this is the broad agenda for today. I'll actually kick things off by just giving everybody a quick preview of distributed machine learning. I think at this point, of course, especially for this audience, a lot of this information might be redundant, but I just wanted to kind of set the stage just so that we're all on the same page. Then I'll give a quick overview of, these frameworks, Chakra and ASTRA-sim, and then hand it off to William, who'll do a deeper dive into the infrastructure itself, and then give a demo on using the infrastructure, and we'll end with some closing remarks and leave it open for questions. In general, of course, feel free to interrupt us. This is a tutorial, so feel free to interrupt us, or of course, feel free to ask us questions at the very end. We'll also be monitoring Slack, but that'll probably be right at the end. We've also provided a link to the tutorial content from today, including a Docker image of the tool itself, the agenda, and the slides. If you wanted, or of course, you could just go to the main ASTRA-sim website as well and access the entire wiki and GitHub. So, of course, AI, the engine driving the AI revolution today is, these AI models, which have shown massive, accuracies across several tasks, right? So we started off with vision about a decade ago, moving on to speech, and today, language, and with generative AI and recommender systems are pervasive everywhere. And really, I think the core of when you're executing any ML workload is you have a model, you have some data. During inference, you would essentially, give these data samples, and the trained model would give you whatever you're looking for in terms of, generating speech or images or text. And during training, you're going to be taking the result, calculating the loss with respect to the ground truth, updating the model. And this is basically called training. So again, just a very, very, very high level view of what training and inference is. Now, one very interesting trend that we've all been following is the fact that ML models are growing at an unprecedented rate. It was about 6.7x per year a few years ago. Right now, it's about 4.2x per year. And there's the other, of course, trend which is hurting us, which is the fact that Moore's law has stagnated. And with just pure technology scaling, we get about 1.35x per year of compute performance, maybe 1.2x per year for memory capacity, and 1.18x of memory bandwidth, right? While we have this 4.2x increase that is coming that we have to really address. And when you're training these models, the other challenge is also there's these huge training data sets that you need to deal with. This is actually, the training data set for Google Bard, which was the precursor to Gemini, which had about 1.56 trillion words of text and code that was used to train it. And in terms of serving models today, again, given all the LLM use cases, there's just a plethora of different use cases that companies to startups to academia has been leveraging from, image to text to sentiment analysis, anomaly detection, code generation, and so on. So from the perspective of this audience, there are several system implications that come in place, right? So on the compute side, you need zeta scale of floating point operations that need to be executed in very, very rapidly. And one interesting number that's used is if you took like a V100 GPU, it would take 355 GPU years to train GPT-3, which was kind of the precursor or the model that launched ChatGPT. On the memory side, just to fit several of these large LLMs, you need, tens of terabytes of memory, which also means that this is not something that can fit on a single device. And you need like, many, many tens to hundreds of thousands of devices to just fit the weights of these LLMs. And naturally, when you have multiple of these together, you have communication that you need to deal with. And again, with these large models and large message sizes, the communication size is also extremely, extremely large. So essentially, to just give you a preview of, distributed ML 101, the key idea is that if I have several of these different devices like GPUs, TPUs, and what have you, we're going to call them neural processing units or NPUs in this talk just for, simplicity and generality. So essentially what you do is you have your data, you have your model, and you're getting, some kind of a result, right? And we can really abstract this into a large matrix multiplication for the purposes of this talk. And what you do when you want to kind of run this across multiple devices is you could either, shard the model itself across the memories of different devices. This is called tensor parallelism. This is needed, as I said, just to even fit the model in several cases. Or you could shard the data samples itself that are being used for training or inference across different NPU memories. This is called data parallelism, right? So you have tensor parallel, data parallel that are kind of the simplest parallelism strategies. There's additional ones that I'll also come to. Okay, so now that you've sharded the model, now you need to communicate between these different devices in order to synchronize data. So kind of taking training as an example, if I have tensor parallel and I have sharded the model across two NPUs, they're both working on part of the model, so they're generating partial results, and so you need to actually perform what's called an all reduce typically or an all to all to get the final result. And that's kind of the key notion that leads to communication. Okay, so with this very quick preview, let's try to understand what these systems that have all these NPUs connected together look like, right? So most AI platforms from a 1,000-foot view look something like this. Typically you have these endpoint server nodes with CPUs with these accelerators and these custom fabrics. And so what you really see in most of these AI platforms is you have these NPUs at the endpoints. Again, as I said, these could be GPUs, TPUs, FPGAs, and what have you. And you have a lot of customized networking fabrics that are used to connect these up together. So kind of from this 100-foot view, we can actually see that, several examples today kind of follow this view, right? So Intel's Aurora supercomputer, AMD's Instinct platforms, Google's Cloud TPU, NVIDIA's EGX, kind of all, can be viewed as, abstractions of this from a bird's eye view. Now, some of the systems challenges anytime you have like distributed training is naturally communication, right? Anytime you have a distributed algorithm, communication is inevitable. And what does this communication really depend on? It depends on the synchronization scheme you're using during training, the parallelism approach. And one question that we often ask is this a problem, right? Is communication a problem when it comes to distributed AI training? And the answer, it really depends. It depends on whether we can hide it behind the compute. So ideally, what we would like is all of these NPUs are fully active, like utilize 100% and computing, in which case, and if the communication can be hidden behind it, that's the best case. However, if there are cases where your compute is just idle because it's waiting for data, that's something that becomes a problem. So how do we actually even determine this? So this is where it's very crucial to understand the end-to-end design space for distributed, deep learning training. And this is a snapshot of what this design space looks like. We've kind of broken it into, three broad layers. We call the first as the workload layer, next as the system layer, and the bottom as the networking layer here. So the workload layer is essentially where you have, your actual workload that you're using, or the DNN model that you would like to train, followed by the parallelization strategy that you employ, followed by the communication policy and pattern that you use. And I'll go into some of this in a little bit of detail over the next few minutes, again, just to get everybody on the same page. Followed by the scheduling. Then you have the actual NPU design itself, the compute and memory, the communication libraries that are being used. So this is where NVIDIA's Nickel or AMD's Rickel would essentially come in. And of course, for this specific audience, like the networking layer, right, which starts from the transport layer to the endpoint node design and connectivity, the specific fabric design, topology, and the network implementation. So, of course, abstractions are great, but then we would also like to co-design this for getting efficiency, right? So there's always this tussle between abstractions and co-design. And I think my purpose in the next few minutes is going to be to give you a glimpse of the challenges across each of these levels of the stack, and then kind of motivate why we decided to model this in order to design next generation platforms. So, okay, so now to just very quickly go through this stack, DNN models are essentially the exact model that you're trying to train. I mean, these could be, your ResNets, these could be transformer models, these could be recommendation models. It basically just boils down to, from a system perspective or a compute perspective, boils down to the specific operators that each of these have. So convolutions, gems, attentions, and so on, right? And the specific model sizes or parameter sizes, which I mentioned could be millions to trillions today. So moving down the stack, you have parallelization strategies. As I mentioned already, right? Like this is basically how do you shard the model and or training data across the memories of different devices. And finding an optimal parallelization strategy is by itself a very, very active area of research today. So as I mentioned, tensor parallel is where you actually shard the model itself and spread it across the memories of different devices. Data parallel is where you actually shard the data samples across the different devices. This is often used to increase training throughput. And whenever you do, let's say, data parallel training, this is the flow of communication that will actually show up, right? So suppose I take the data samples, shard them across the memories of different NPUs, and each NPU has a copy of the full model. Then they will essentially generate, the inference results during the forward pass for their specific data sample. So there's no communication during the forward pass. And during the backward pass, what's going to happen is they're going to start computing gradients. And so they're going to compute the partial weight gradients, synchronize these to get the full weight gradients, compute the input gradients, and kind of, this becomes the gradients for the next layer. Right? And so one of the key communication requirements here is, since each of these NPUs is generating partial gradients, you need to actually synchronize them. And which essentially means, since each of these NPUs has generated, partial weight gradients, you basically need to add them up to get the full model. Because remember, in data parallel, everybody needs to have a full copy of the model. So for the next training iteration, you need to synchronize this so that everybody has the up-to-date copy of the model. And so you need to kind of sum this up and then have everybody get the final copy. And this is what is the communication that we often have to deal with. And again, I'll go into this in a little bit more detail in a second. Okay, so now I have, data samples that I've sharded across NPUs. I need to communicate how do I communicate, right? So again, there's two broad ways of doing this. So one is called parameter server, where you have a centralized server whose job is to actually accumulate these gradients together. So in this case, I have these three nodes here. Each of these is going to send the model gradients to the central parameter server, and this will, accumulate them and then send it back. This is, of course, easy to see and understand. But naturally, just like any centralized solution, this parameter server can start becoming the bottleneck. Which is why what's actually done a lot today is to do this in a purely distributed manner using what are called collectives. So here in a peer-to-peer manner, we would like all of these NPUs to still perform the weight update or the weight gradient update, but not have to send all of this to a central node. And this is where you use collective communication. Of course, collective communication is something that has been pervasive in HPC for decades, right? And so essentially, these are some of the collective communication patterns that are quite common in AI training. You have reduce scatter, where, as the name suggests, you basically do a reduction of the partial gradients and scatter the results across the different NPUs. All gathered is where you have, let's say, some data across all the NPU memories, and you just kind of broadcast it so that everybody has the up-to-date copy. What's actually done for, especially in data parallel, for getting the final gradients is what's called an all reduce, which is basically nothing but a reduce scatter plus an all gather, where everybody at the end of this iteration has the up-to-date copy. You have done a reduce scatter and then broadcast it to everybody. And you also have all-to-all patterns that show up in certain parallelization strategies, where, as this suggests, essentially every NPU is sending data to everybody else. Okay, so now in terms of communication, during the forward pass, as I mentioned, there is no communication for data parallel training because everybody has a full copy of the model. But during the backward pass, you actually need to perform an all reduce collective. So what ends up happening is, you compute the input and weight gradients, you synchronize these weight gradients using the all reduce, and then the input gradients, of course, just going forward, the weight gradients again getting computed, synchronized, and so on. What's nice is this is actually a non-blocking collective for the most part, except at the very end where you have to wait for everything to finish before you can start the next iteration. So this is just an example of data parallel, right? So just with data parallel, you already have this kind of communication flow. But as I mentioned, there's a lot of different kinds of parallelism strategies that are actually being used in practice today. So Microsoft Spike Dream, Megatron, LM, FSDP are all different kinds of parallelism strategies. And as I mentioned, this is a very, very active area of research by itself on how do you, if you have like these thousands of GPUs, how do you actually shard your model weight? So typically you do like a model like a data parallel, tensor parallel, pipeline parallel, and especially with LLMs, you also do sequence expert parallelism strategies, right? So just again, I won't go into a lot of the detail, but the basic abstraction is depending on the parallelization strategy, there is a certain communication or a collective communication pattern that we need to deal with. Okay, so that's kind of the workload layer part, the workload part of the distributed training stack. Now let's look a little bit at the compute and memory part. Here, again, as I mentioned, the key thing to keep in mind is, there are certain operators that we need to run, and matrix multiplications are the most, prominent operators that are being used, given that, neural networks ultimately are doing a bunch of dot products, and with batching, it becomes matrix multiplication. And of course, there's several different, hardware accelerators out there. Some of them kind of use, SIMD units as their building blocks. Some of them use systolic units. Again, this is a whole domain by itself. But ultimately, the aim is that, we would like to add specialized support for these, matrix multiplications and try to maximize hardware flops. Now, again, what's interesting is that as you design accelerators or these NPUs to be more and more efficient in terms of compute, like, you have like things like sparsity, 2:1 sparsity support that NVIDIA added and so on. What ends up happening is that your accelerator NPU becomes more and more efficient, which means that communication becomes even more of a problem because your accelerator is just so efficient that it needs like these gradients much, much sooner, right, in order to accumulate. And so this is just an example from, in fact, our simulator itself, which shows as your compute power, increases, the exposed communication. This is the communication that you're not able to hide behind compute starts going up. Okay, so now that you have this communication, how do you actually schedule this communication across the different NPUs? This is where you have libraries like collective communication libraries like Nickel, Rickel, MSICL that all come in. And essentially what they try to do is they try to come up with collective algorithms or topology-aware collective algorithms, which are basically algorithms for implementing the specific collective pattern. So as an example, if you have an all reduced pattern that I had shown earlier, there can be several different ways of running that all reduce across different NPUs. So ring, direct, halving, doubling, Rabin Siphoner, double binary tree, and so on. And so basically, given a specific network topology, an efficient mechanism to run the collective communication exists, which is called a topology-aware collective. So as an example, suppose I have four NPUs that are connected together as a ring physically. The most optimal collective algorithm for running all reduce on this is what's called a ring-based all reduce, where what you end up doing is suppose you have this system with n nodes, like four nodes in this case, we actually partition the all reduce we need to do into four messages. And then remember what we need to do is ultimately perform a reduce scatter and an all gather. So what happens in a ring all reduce is each of these NPUs takes this, one of these chunks and forwards it to the neighbor, and all of them do it at the same time. So node 1 forwards chunk 1, node 2 forwards chunk 2, node 3 forwards chunk 4, and node 4 forwards chunk 4. And you add it up to your local, gradient of that chunk, and so on and so forth, right? So then you forward 4 here, 1 here, 2 here, 3 here, and so on. So in 3 steps, what's happened is everybody has forwarded, parts of the chunk, and we've now performed a reduced scatter. So mathematically, what's happened is there has been a reduction of these different, messages, and they have been scattered. And an all reduce is a reduced scatter followed by an all gather. So now what you simply do is take this, updated chunk and just keep a copy and forward it to your neighbor. So you keep a copy, forward it to your neighbor, right? And whatever you receive from your neighbor, keep a copy, forward it to your neighbor. So again, in this case, 3 steps later, an all gather is performed and an all reduce has been performed. So what's beautiful about this algorithm is at every time step, you'll notice there was some message on the ring and there was no congestion, right? So that's kind of the beauty of these topology-aware collectives. Like ideally, they try to give you congestion-free, performance and extremely, extremely high utilization. If you, instead of having a ring, suppose physically all these NPUs had like a fully connected network connectivity between them, then instead of performing a ring all reduce, which would still work, you can actually do what's called a direct or a one-shot all reduce, where you just in one shot send a copy of like all of these chunks to your neighbors because you have direct links to them, perform the reduce scatter, and then in the next time step simply perform an all gather, right? So this is what's called, as I said, a direct or a one-shot all reduce. And similarly, there's another algorithm called halving doubling, which is used where you kind of do it in a logarithmic manner, in a tree-based manner. So for different kinds of topology building blocks, like for a physical ring, you have a ring-based algorithm. For a fully connected network, you have a direct algorithm. For a switch-based network, halving doubling. There's different algorithms that are optimized for each. And as I said, this is what's called as a topology-aware collective algorithm. But this really depends on the physical topology. If you have a 2D torus, you could in principle run a ring-based collective on this, but this will naturally underutilize several of these links. So then what ends up happening is for more sophisticated topologies, let's say like a torus, you do what's called a phased, or a multi-dimensional collective. So you do kind of you reduce scatter across one dimension, followed by reduce scatter across the other dimension, followed by the third dimension, and all gather across all these. And you kind of do this in this phase manner, and then you pipeline all these chunks to increase utilization. Right? So this is an example of multi-dimensional collective. Okay, so that was kind of just a glimpse of what happens on the system layer, right? Then we come down to the actual network. So you have these collectives, you have these messages that are logically going across in this manner, but now the actual performance depends on your actual physical system. And one open question is, how do you design the next generation system? How do you even connect like hundreds or thousands of these NPUs together? And so just to kind of give an example, today there's a lot of different networking technologies that are at play, right? So people are looking at chiplets and advanced packaging, to, wafer scale, in integration. There's a lot of different rack scale interconnects that are being developed, NV-Link, XC-Link, and like the most recent excitement around UA-Link. And then of course there's, InfiniBand, Ethernet, or even like, optics that are used often to scale out. So what ends up happening is you can end up with these very hierarchical, network architectures where maybe you connect a bunch of NPUs together on a package, followed by a rack scale interconnect, followed by, like a rack to rack interconnect, and scale out via NICs. And so again, if you look at some of the systems today, you can kind of you can abstract them into things like this, right? So you have the NVIDIA SuperPods, which are multi-level switches. Tesla's Dojo actually uses like a scale-out mesh network. I mean, it has like multiple of these on a package followed by scale-out. Google uses like a 3D torus, and it also has then an optical scale-out dimension as well. So state-of-the-art training clusters, like, again, from different companies, right, essentially are becoming more and more complex with several different, kinds of network fabrics that are being used, which also makes it challenging to kind of understand and study all of this together. And finally, on the network implementation side, there can be several different, there can be a lot of microarchitectural effects based on, this is again an experiment we did with ASTRA-sim, where we were trying to understand the impact of switch sizes on training performance. And again, the takeaway here, without going into details, is depending on your connectivity and switch sizes, your performance and like the exposed communication can vary. So essentially, the key takeaway I kind of, something that I would typically even teach like in a full semester. I'm trying to combine it, like, compress it into like a quick, just a quick preview of the landscape of distributed ML, right? Where large-scale distributed machine learning is an open research area, but many emerging supercomputing systems are being designed specifically from this problem. And there is a huge co-design space here across software and hardware. And co-designing offers a lot of opportunity, but each of these independent, design spaces is already quite complex, right? Starting from the workload to the system to the network. So this really kind of, motivates. I mean, the aim of this part of the tutorial is just to kind of motivate why we are even trying to build an infrastructure to understand and study this design space. And I hope I've kind of managed to do that. So with that, what I'm going to do now is jump over to the meat of this tutorial, which is to give you a preview of the infrastructure we are developing for modeling and studying this design space. So just to again, set the context. So far, what I did was give you an introduction to distributed machine learning. And now what I'm going to do is give you an overview of the Chakra and ASTRA-sim infrastructures that help you understand, model, and benchmark and study this large design space. So again, just to recap, right? What I mentioned was there is a complex software hardware co-design space, right, for distributed machine learning. On the workload side, as I mentioned, there's DNN models, parallelization strategies, the framework level policy and pattern. On the system side, you have your compute communication mechanism, the collective scheduling strategy across collectives, and the exact collective algorithm, or the topology-aware collective algorithm. And then you interact with, the actual compute, which is where this is kind of your NPU microarchitecture, if you will, the operators it supports, the data flow, the mapping, like the number of processing elements, buffer sizes, and so on. The network fabric, which involves the network topology, the connectivity, the network implementation. And in fact, given that things don't fit in a single memory, there can also be architectures that leverage remote memories, right, via things like CXL, which introduces a whole new landscape of memory systems to handle that as well. So how do we model and this complex design space? So this is where we've actually been part of like two efforts to address this challenge. So the first, which focuses more on the workload side of things, is this effort called Chakra execution traces that I'm going to talk about. This is an open graph-based representation of AI/ML workload execution. And the second is the ASTRA-sim simulator, which is basically a simulator for modeling this distributed AI platform and capturing the impact of the co-design space, which includes the system, the compute, the network fabric, and the memory, and of course the interaction with the workload. All right, so let me start with the Chakra execution trace view of the world and like what exactly this is. So the motivation for actually Chakra comes from this observation that co-design is actually a loop, right? Where what ends up happening is if you have, let's say, if you are a company, let's say you're Meta, right? You have, these systems that are deployed. You observe some performance, in production, right? You have some performance that you're getting training or inference of your AI models. You would like to, reproduce them via some representative benchmarks, maybe identify opportunities for improvement, and then you maybe want to enhance the software stack or the actual hardware in terms of the NPUs or the fabric and so on. So you would often like to first design it and evaluate whatever you're trying to propose with some simulator or emulator, test it out again with some representative benchmarks, build it out, deploy it, scale, and then again you kind of observe what happens and this loop kind of continues. Now, one of the challenges with realizing the software hardware co-design loop is that there's a very, very high cost for running full workload benchmarks, right? I already mentioned, you need like thousands of GPUs today just to even like run a representative training run, which is very expensive. Even for big companies, it's expensive. And, once you have startups and academia, it's kind of almost a non-starter. You also often require a lot of cross-domain expertise because deploying these models, requires expertise across the model frameworks themselves, the compiler stacks, and like whatever low-level, runtimes are available for your hardware accelerator. So it becomes very, very challenging. It also becomes very difficult to isolate specific bottlenecks on the hardware or the software side, right? So you see certain performance. Is it because of the fabric? Is it because of the NPU? Is it just because of some library, or is it because of the collective library? These are things, or is it things at the model level? It becomes very, very hard to isolate. And it often becomes hard to keep up with the pace of AI innovation, right? People are kind of developing models left, right, and center, new models coming out. And so this becomes extremely challenging. It's also very often hard to obfuscate proprietary AI model details. What do I mean by that, right? So this ecosystem actually has a lot of different players, right? There's companies that are developing models, there are hardware vendors, there's fabric vendors, and not everybody is comfortable sharing like full model details, right, with everybody. And so you want to kind of you would ideally like to share enough details so that your vendor can design the right fabric or the NPU for you, but there is hesitation in revealing a lot of specific body details. And ultimately, in all of this, it's very hard to reproduce these things without support infrastructure. So again, I'm sure like for a lot of the people in the audience, like you kind of encountered at least one of these issues, if not more. So to address this, we started this effort called Chakra Execution Traces, where the key idea was to try to capture the behavior of distributed AI models as a graph and as an abstract graph where it's capturing the specific things you need for designing systems, not for like running end to end. So we would like to capture the compute, communication, and memory behavior of, let's say, distributed AI models. So that's kind of what the Chakra execution trace captures. It's a hierarchical DAG with nodes that represent compute, communication, memory accesses. The edges represent data dependencies and like control dependencies. And you can have like higher level abstractions as well. But the idea is this is not like this is not the exact full model. This is capturing the key components that you would need for designing systems for this. And so this is kind of part of this larger ecosystem that we've been building, where the goal is that we would like to capture these Chakra traces from real production workloads, capture them kind of in this form, right? Like all the compute, communication, memory behavior with timing. And then, so this part is, might often be proprietary because, you have every company has their, production workloads and their own models. And then we have this community-driven open infrastructure where we're trying to create the ability to, take these Chakra traces, visualize them, analyze them, maybe even, synthesize them synthetically, and then take these traces and either feed them back to your current systems and just replay them in order to do, maybe debugging or performance optimizations. Or you could take these traces and feed them to a simulator to design a next generation system. And these simulators could be open source like ASTRA-sim that I'll present today, or they could be internal, proprietary simulators. So with this kind of view, the idea is if we can create a mechanism to capture these real traces, then once we have these traces, we no longer need to run the model end to end to do all of the co-design studies that I mentioned, right? So now you can take these traces and do a lot of your performance optimizations for just getting better performance from your current system or design next generation system. So this is, as I said, part of ML Commons now. This is a community-driven effort. We have several different companies that are, part of this. I'm sure many of you in the audience are aware of this, if not already participating. Essentially, we're trying to build consensus on the execution trace methodology so that we can enable easier sharing between hyperscaler clouds and vendors with and without NDA. We can have, different people in the ecosystem focus on different individual components, whether it's compute, memory, fabric, and enable, faster ramp up for startups and academia. We're trying to get like a shared engineering effort, right, towards this open and vibrant ecosystem. So together with, again, academics and industry, we're trying to come up with a mechanism for trace collection and synthesis, and support downstream tools and enable, these to run with downstream, like downstream tools, which could be, again, open or proprietary. And we're also working towards eventually creating a benchmark suite of these Chakra traces, which is kind of where, ML Commons and ML Perf comes in, where we would like to then release these traces to the community. And so this has been so again, feel free to check out our website. We launched about 1 year ago. And at this point, we have a very, as I said, active working group. We meet about, once every 2 weeks and kind of go over all of these different components from describing the Chakra schema itself to, updates in PyTorch for collection to mechanisms for replaying this on current systems to, simulating it, and even mechanisms to, create these traces synthetically. Again, so I'm happy to talk about Chakra itself in more detail in the Q&A. So that's that's the Chakra piece of the puzzle, right? So let's say we have now this mechanism to describe distributed workloads in this graph manner. Now, this is where ASTRA-sim comes in, which is going to take these and help you simulate and design next generation systems. So one of the key things in ASTRA-sim is that we want to, so I presented kind of this design space, right? ASTRA-sim tries to capture this design space faithfully. And one of its key novelties is that we basically provided a bunch of APIs to plug in diverse external tools into ASTRA-sim. So ASTRA-sim is not a standalone simulator itself. It's not like a Gem5 or an SST. Think of ASTRA-sim as a mechanism where you can plug in your own, individual simulators. Let's say, I want to plug in like the network fabric from SST. I want to plug in like a, my fancy NPU simulator, which is proprietary. And I want to, let's say study, I have my own collective algorithm that I want to integrate. So you can kind of plug in all of this and kind of create the infrastructure that helps you then study the system you would like to study. So that's kind of the high level view of ASTRA-sim. So what we have today, I really view it as a reference implementation. But I can again want to emphasize that the main value is all of these APIs, and in fact, several people who are using it are actually using it via these APIs, as I'll describe next. So this is kind of a high-level overview of ASTRA-sim, right? As I mentioned, it's trying to capture that design space very faithfully: the workload layer, the system layer, the network, remote memory, and compute. So the workload layer will take the Chakra execution traces as an input. It parses them, identifies the individual operators, and then sends them over to the system layer. Right? That's kind of the high-level goal of the workload layer in ASTRA-sim. The system layer is going to initiate the exact like compute, memory, and collective operations. And the collective algorithms are implemented within the system layer. And we'll talk about this in more detail later. And then you pass on these events to the compute, memory, and network simulators. The network simulator, as I mentioned, is one where you plug in your own network simulator via an API. And so, today we have an analytical version. We have Garnet from Gem5, we have NS3, and some of the users of ASTRA-sim in different companies have plugged in their own network simulators as well. And again, depending on, how much fidelity you need, you can kind of plug in a simulator for modeling what you would like to do, right? So if some folks are interested in studying RDMA, they can let's say use an S3. If you're simply interested in studying topologies, you could use a different simulator. So that's the network simulator, right? The compute one is again similar, where the vision is that you plug in your own compute model, right? So you could, you might just want to use a roofline model, or you have your detailed GPU simulator, or you have your fancy, NPU that you want to study, right? So we actually support some of these. We have a roofline model, we have scale sim, which my group had developed, which models more like a TPU-like system, or you can plug in your own compute simulator as well. And similarly, for modeling like disaggregated systems, we also provide like a remote memory API where you can potentially model and study, disaggregated memory architectures. So to conclude this part of the tutorial, just to summarize, there is this complex design space of distributed AI ML training and inference, which includes the workload, the system, the compute network, and memory. And the Chakra execution traces are a mechanism to capture the workload behavior as a graph. And this is an effort that we are involved in to describe what these traces, the trace format should be, and create an ecosystem which includes these benchmarks. And ASTRA-sim takes these workload traces, and it is modeling the nuances of the distributed AI platform from the system layer, or the system software layer, to the exact compute network and memory hardware that you would like to study, which are plugged in using APIs. All right, so with that, I'm going to now hand it over to William, who will do a deeper dive into the actual simulator itself.
Thank you so much, Tushar. Let me start with sharing my screen. Hopefully my network layer slice is visible to everyone.
Yes, we can see your slides.
Yeah, thanks for checking. Sorry, I'm suffering from COVID right now, so my voice is a little bit hoarse and choppy. Please excuse me for that. My name is William Wan, PhD student at Georgia Tech, advised by Dr. Tushar Krishna. And as introduced, I will go to the deeper dive into the actual ASTRA-sim and Chakra infrastructure in more detail. So with that, this very slice is talking about the deeper dive into the workload and the Chakra infrastructure, and which talks about the design space of the workload here, about DNN model, periodization strategies, and framework policy patterns, and so forth. And in the ASTRA-sim side, the workload layer, which receives Chakra execution trace as an input, then parse it and dispatch it to the underlying system layer, is exactly developed in such a way to model the workload design space in the most faithful manner. So the job of the workload layer is to capture the workload specific characteristics, as I mentioned, things like DNN model itself, the periodization strategies used to train a model, the control and data dependencies between each and every operations, and the ordering of compute and communications, and so much more. And in ASTRA-sim, especially the 2.0, the current version we are using, all these workload characteristics now are being captured through MLCommons Chakra execution trace representation. And as Tushar briefly mentioned, this is a standardized distributed machine learning workload representation, which is being driven by the ML Commons community. So anybody's encouraged to join the ML Commons working group and read the paper, contribute to the paper, and contribute to the ML Commons GitHub project, and so much more. And yeah, as briefly touched upon, the Chakra ecosystem is that we have this entire flow to represent the distributed ML workload in Chakra. Then the simulators, downstream simulators, for us, the ASTRA-sim can receive the Chakra, which already captures the entire workload representation, and use it for useful simulations. The basic structure of Chakra execution trace is that Chakra execution trace has three types of basic nodes, which you can see as a basic building blocks. which is defined in the Chakra schema etdef.proto. The three basic building blocks we have in Chakra execution trace is compute, communication, and remote memory, which, as the name suggests, captures the compute behavior, communication behavior, and the remote memory accesses, especially thinking the big scale remote pooled and disaggregated memory systems. And the reason we capture the end-to-end distributed ML workload in these three nodes, not more finer grained, is because we believe that the distributed ML, where the gem time and several compute kernels and the collective communication is dominating the entire end-to-end execution time. So we believe these three nodes, when combined, can precisely yet very concisely capture the end-to-end behavior of any arbitrary distributed ML workloads. So going into further detail, the compute node encapsulates the compute operation happening in the distributed machine learning. Mostly matrix-matrix multiplication, but also we can capture other kernels such as activations like ReLU, softmax in this compute node. So the compute node attributes you may think of is the number of floating point operations to run, or an attribute such as to note whether this is happening over a CPU or other devices, and the tensor size of inputs and outputs, or an additional embedding of the estimated or actually measured computation time to run this compute kernel, and so forth. Whereas the communication node captures any communication behavior happening in the distributed ML execution, which can be either a single send and receive pairs or usually collective communications, including broad MPI collective communications, including all reduce, all gather, reduce scatter, or even broadcast, reduction, so much more. So here in the communication node, you can think of attributes such as the communication type, the communication size, and the involved NPU devices, or even the priorities of the communication. And for remote memory node, it's likely we use this node to capture the remote memory behaviors, such as fetching some data from a remote memory or dumping some data to a pooled memory. So that's why we can think of attributes such as the tensor's location and the tensor size. And Chakra is very versatile. You can embed arbitrary attributes to an existing node. So the bullet points I showed here, the basic attributes we can think of to embed to the Chakra ET. And the end-to-end Chakra execution trace is nothing but an arbitrary directed acyclic graphs where you instantiate all the operations happening in the distributed ML execution in remote memory, compute, and communication operations, and then assigning the dependencies between among the Chakra ET nodes. So for example, this Chakra ET shown here kind of means that the first operation happens is a remote memory access from device 3 of size 500 megabytes. Once this is done, two operations can run simultaneously, which is one gem and another gem with different size. And then here you can see once this compute operation has been finished, another two kernels can happen simultaneously. One is the collective communication of all reduce of size 100 megabytes, or another different gem operation. And likely here is shown a dependency once this compute operation clears that the remote memory access or another communication can happen. And you can think of basically very complex Chakra execution traits still consists of the remote memory, compute, and communication nodes, and they can concisely, but at the same time, very accurately capture the end-to-end behavior, the workload behavior happening in the distributed ML execution. So this is the Chakra execution traits. So this is a more detailed, deeper visit of the example Chakra execution trace. So this is a section of the actually visualized Chakra execution trace we collected. And as you can see, these dense means some dense gem operation, and there's some receive and send operations. So all these nodes combined can, again, capture the end-to-end workload behaviors of distributed ML. And if you zoom into the one compute kernel and zoom in their attributes, you can see Chakra ET, one Chakra ET node carries some trivial metadata, such as the node ID, the node name, the node type, for this case, collective computation node, the dependency, meaning this node is depending on other Chakra node whose ID is 5525, and trivial size information such as, because it's a computation node, it carries input information such as the shape of the tensor, the number of input elements, same for the output elements, and also additional attributes as we wish to attach and carry. So for this case, we attach the additional attributes saying this is the CPU operation. So you can think of a Chakra execution trace in actual implementation is a list of all these Chakra ET nodes tightly combined by the data dependency and control dependency characteristics. In generating these Chakra execution traces, we can think of basically three big branches of it. One is manually, but at the same time, very flexibly generate the Chakra ET generation API. But because just using the generation API to generate very complex workload can be very tedious, a lot of work has been creating the wrapper or automation to call this API to support more complex end-to-end workload generation. And in the demo, we will cover the text-based and synthetic end-to-end Chakra AT generation flow. And also one big branch is actually profiling and running the actual PyTorch execution from a real system and collecting the Chakra execution trace from it. So all these three bullet points to generate the Chakra execution trace will be covered in the later demo session. And once the Chakra is given to the ASTRA-sim, how do we parse and use it is being done by this infrastructure called ET-Feeder. ET-Feeder offers us clean APIs to read and manage these Chakra ETs, which is defined in the Chakras etfeeder.h. But here I'm just introducing two very notable and very important ET-Feeder API, where the first is get next issuable node. And as you can see, the name suggests it returns a free ET node that doesn't have any dependency anymore and can be dispatched it can be dispatched at the time. And another important API is free children node. When the node ID is given, it marks that node as finished operation and free the dependency so that the child node can proceed to the next stage. So how the ET-Feeder API work in real action is that if you recall the example Chakra execution trace, when I call the get next issuable node API for this one, this API will return me this node because this one doesn't have any dependency and can be dispatched. And when I call the free children node for this remote memory, then it will be marked as finished and the dependencies of these will be freed. So as you can see now, when the remote memory node is freed and finished execution, now these two operations are a issuable node because this doesn't have any dependency, any unresolved dependency anymore, and can be dispatched. So when you call a get next issuable node again, it will randomly give you one dispatchable node. So for this case, I just selected this one. So get next issuable node will return you this compute node because again, this can be dispatched and doesn't have any unresolved dependency anymore. And if you call the free children node for this compute node again, it will be marked as done and the underlying dependencies will be resolved again. So that for the given scenario, now we have three lists of issuable nodes. And when I call the get next issuable node again, one Chakra ET node among the three will be returned to me. So ASTRA-sim is using this API to parse and execute the simulation when the Chakra execution trace is given. So this is the pseudocode of the ASTRA-sim's workload layer. Basically, until the simulation finishes, what we do is query the ET-Feeder to give me the get next issuable node and issue the simulation of it. And once the simulation of this specific node is finished, then we by using the free children node API, we mark it as finished and free the children's dependency so that we can get more list of next issuable node. And by iterating over this until the simulation finishes and until everything is marked as done, this is how ASTRA-sim is parsing the Chakra ET using the ET feeder API and running the end-to-end simulation. So this is the actual snippet of the implementation in the ASTRA-sim's workload layer. It's a little bit more complex, but as you can see, this is very much the same as the pseudocode I just showed right before. So here we actually query the ET feeder, get next issuable node API to get the node, and we check whether the hardware resources available because we don't want to run n number of operations to happen simultaneously because we want to simulate one node at a time. That's why we check whether a hardware resource is available or not. If it's available, we issue the node. If not, we basically push the node back to the Chakra ET. And basically, we repeat this multiple number of times because here, as you can see, we're currying the get next issuable node, and this snippet is being repeated infinitely until the simulation ends. So this is how the ASTRA-sim's workload layer is parsing the Chakra ET and dispatching one operation at a time. And here, as you can see, the issue is the actual method to kickstart the execution, the simulation of the of the given Chakra node. So here, let me go a little bit deeper about this issue method. The issue method triggers the appropriate ASTRA-sim simulation methods. So here, by appropriate, I mean this is a very simple snippet. The workload issue method, it basically checks the Chakra node's type. So if it's a remote memory operation, it just delegates the work to the issue remote memory. If the node type is computation, we just delegate to the issue computation. As you can see, this is nothing but a switch mechanism checking the Chakra ET's node type and calling the appropriate issue method. So for here, let me visit the issuing computation real quick. So what the issuing computation happens, what it does here is that it calls the roofline model existing in the back and register an event handler. So going a deeper dive into the issue computation, what happens is that, again, because we don't want multiple computation happen at the same time, we mark the hardware is now occupied so that not the other Chakra node can be run until this computation is done. Then by calling the roofline model, ultimately, we want to estimate how long by running a roofline compute simulator, we want to estimate how long this operation will take. So by, again, calling the roofline, we have estimated how much time is required to run this computation node. Then basically, we register an event about this runtime after this runtime saying this to block out that this compute node will take this much amount of time. And here, as you can see, as the current ASTRA-sim infrastructure is kind of defaulting to the roofline model. And at the same time, we acknowledge that the computation is its entire own research area and design space. That's why here, as a very sneak peek, and the current roofline model kind of assumes it by having the peak performance and in number of teraflops and the local memory bandwidth as an input, but we still want to give more flexibility. That's why we are developing a new API called Compute API and also developing a very new layer called Compute Layer. So with this update, instead of just defaulting to the roofline model, here we will just delegate to the simulator by using the API called Simulate. Here we will just pass the nodes compute kernel information and just let the compute simulator simulate this node instead of just using roofline again, and let the ASTRA-sim know by calling this event handler back. So this will give us the entire flexibility to plug in arbitrary compute simulator instead of just defaulting to roofline or analytical model and to let us simulate, to let us use any arbitrary simulator that we wish. The compute API work is in progress. We have created a pull request, so you can expect this effort to be merged in pretty soon. Going back to the issue mechanism in the workload, we just covered how to issue computation. The communication is very simple and very similar. So here, the issue communication operation, what it does is, as you can see, similarly, we occupy the hardware resource so that no communication is happening simultaneously. And then here, we just delegate the communication simulation by calling this generate all reduce op API, which is defined in the system layer, which I'll cover in the very next session. And then once this generate all reduce simulation is done, ASTRA-sim is requesting to call this notifier collective communication finished once once the simulation of this communication node has been done. And what the event handler that both the issue computation and issue communication wants to receive is that because we occupied a hardware resource, when the event handler is being called, we want to release it and free the children node and want to dispatch more nodes because now one node simulation has been done. So this is the code snippet of the event handler. Here, as you can see, we are releasing the hardware resource for the node. And because the simulation of this node now has been done, we are freeing the children node of this node. And we basically enter that dispatch of free Chakra node again. So ASTRA-sim's workload layer is the combination of all these. By dispatching the issuable Chakra node and calling the right compute or communication simulation, then once the simulation is done, releasing the hardware resource, freeing the children node, and issuing the dependency-free node back again until everything is done. This is how ASTRA-sim's parsing the given Chakra ET and running the simulation. So this was the deeper dive into the ASTRA-sim's workload layer, which guides me to the deeper dive of the ASTRA-sim's system layer, which is right under the workload layer, where we have to simulate operations such as compute communications, overlapping and mechanism, collective scheduling, and collective algorithm. So ASTRA-sim's system layer is sitting in the middle of workload layer and the network layer, orchestrating the operation of the workload issue communication and the network's actual network behavior simulation. And for the future compute layer or orchestration as well. So this is where I stopped in the last slides, where when we issue a communication in the workload layer, we occupy a hardware resource and delegate the system layer to generate this all reduce, which is the job of the system layer. And in this slide, in this deeper dive, I will just go and give a example of how this generate all reduce is being performed. System layer is where this issue collective communication algorithms are being implemented. But after the system layer operation, all these all reduce, all gather, those MPI collective communications will be broken down into individual chunk send and receive. Those will be processed by the underlying network layer, by the actual network simulation. And the breaking down of the collective into chunk send and receive will be managed by finite state machine mechanism. So for example, I'll go the deeper dive into the how actual the generate all reduce is working. So in the system layer, each GPU maintains this finite state machine, and these finite state machines shown here is the FSM for the generate all reduce. And currently we are in the initialization stage. And now when the issue all reduce function method has been invoked, it will dispatch this. Following the implementation of the algorithm, it will dispatch some send and receive messages and be in the stage of wait for the receiving to be done. Then the actual send and receive will happen under the underlying network layer, which I'll cover next. And once the event handler that the send and receive has been done is being invoked, this message of finished will be triggered. And now when the messages has been reached the destination but we know that the collective communication has not been finished yet. So we're going back to the stage of the init. Then we basically repeat this until we know that the all reduce has been finished. So by repeating this back into the init, issuing the send and receive, wait for the receiving, wait for the reduction, and going back again because the all reduce is not being done, and another set of send and receive, and then waiting for the receiving, waiting for the reduction. Now here we know the reduce scatter has been done. So the next stage implemented to enter is not the init, but actually the next stage. So here, because the finite state machine recognizes that the reduce scatter has been done, and now we should run all gather, it it dispatches the send and receive based on the predefined ring-based manner. So it dispatched the send and receive message, and again, wait for the network, simulates this send and receive, and the receive handler is being invoked. So while the finite state machine is waiting at the receiver stage, the send and receive happens in the network layer, and the actual network simulation is happening. And once the messages reach the destination, they invoke the event handler. And again here, because the finite state machine recognizes that the number of messages it should receive is not being fully received yet, it just iterates over here and dispatch another send and receive message until the all gather is fully done. So here it dispatches another send and receive, wait for the receiving to happen, and the network layer will simulate everything. And once the receiving is happened and the event handler is being called, again it enters this path and dispatch another send and receive operation to the network. Then when the simulation ends, now we know that n-1 number of messages are properly being received. And that's when the finite state machine exits this stage and enters this done stage where we know that the entire simulation of all reduce is being done. So maintaining this finite state machine and dispatching the send and receive on along the way from the init stage until the done stage is how actually the generate all reduce method I showed in the workload layer is being executed, and actually how the send and receive messages along the way is being generated. So this is the job of the system layer, where the generate all reduce operation is given following the finite state machine, send a bunch of send and receive operations to the network layer and enter the dawn stage, and basically repeat this multiple number of times whenever the workload wants you to generate new collective communication. So so the system layer also does another operation such as collective level scheduling, which I haven't covered in this deeper dive, but that's why in the system input, you can see operands such as the scheduling policy between different collective communications. It also manages the delay of each endpoint, and also how many number of active chunks will be there, and also how many chunks you want to generate per each collective communication. Whether do you really want to simulate the entire finite state machine for every GPU, or if you just want to simulate GPU 1, assuming that's much faster, and also which all reduce or all gather different MPI algorithms you want to simulate. So you can see that system layer is really orchestrating the job of the workload layer and splitting the collective communication into different send and receive and dumping into the network layer so that the actual network simulation can be handled. And again, as a sneak peek of our future work, we recently acknowledged that there has been a lot of work in the collective algorithm side itself, where, as an example, this MSQL-lang is a high-level high-level design-specific language to represent collective algorithms. So for example, this is one collective algorithm represented in the MS-SQL-lang. And at the end, this XML operation will dump it in a standardized XML format. So now this XML format itself can carry the collective algorithm information itself. And acknowledging that, we're augmenting the system layer to use these kind of custom algorithms as well as the ASTRA-sim's native algorithm and finite state machine as I shared. So this work is in progress, and we just had the hot eye presentation just yesterday. So when ASTRA-sim, when upgraded in a few moments, will be able to receive custom collective algorithm plan in XML and bypass the ASTRA-sim's native FSM-based implementation and be able to simulate the custom algorithm. The system layer should be able to support the simulation of these custom algorithm, dispatch it to the network layer to enable the end-to-end workload simulation. And this is another sneak peek of the generation side. So we have a work to appear in Micro 2024, which is the mechanism to quickly generate custom collective plan, which is called tacos. And again, merging all these efforts into one, tacos can generate the custom collective plan, which can be supported by our new collective API effort, which can be simulated with the updated ASTRA-sim's infrastructure in an end-to-end based manner. So these are the sneak peek of what will be to come in the future ASTRA-sim, and we are actively pushing the effort to the mainstream branch as well. So this was the deeper dive into the system layer. And the only remaining deeper dive I have today is the tour into the network layer, where the workload has been parsed, and in the system, the communication is broken down into single send and receive. And the network layer is exactly what captures this single send and receive and simulate the actual network behaviors, such as the underlying network topology, the network connectivity, and the network implementation. And this design space is being captured in the ASTRA-sim's network layer, which is augmented to the entire ASTRA-sim flow using the common network API structure. So just to reiterate, this ASTRA-sim's network layer simulates the actual network behaviors, which can be very deep and very detailed, such as communication protocols, network topology, bandwidth and latency, or even in-network collective communication support, the NIC offloading, compression, buffering, arbitration, and all the other network behaviors such as flow control, congestion management, and so much more. And because we want versatility in terms of modeling different network behaviors and statistics, that's why we come up with a common API called Network API to support a more plug-and-play based manner of network simulations. So the Network API is the bridge between the ASTRA-sim system layer and the underlying arbitrary network simulators. So by having this network API, just like the compute API, we can give the flexibility and versatility to plug in any network simulation, any network simulator infrastructure you want, rather than just using what ASTRA-sim wants you to use. So that's why we have created the network API and plugged it in and then used it in the ASTRA-sim to plug in different network simulators. And this is the example notable network APIs I want to bring in this tour for today. SimSend is an API that system layer uses to request the network layer to simulate a send operation from this source GPU to this destination GPU with this much message size. And once done, request you to run this callback so that the system layer recognizes that the send has been finished and can run the finite state machine accordingly to proceed to the next stage. Same for the sim receive. This API is being run by the system layer to request a receiving simulation from MPU source to MPU destination with a very specific message size. And again, once done, request to invoke this callback so that the define estimation recognizes. SimSchedule is a more simpler API where instead of simulating an actual network behavior, just request to call a callback after a delta time. So this is a simple API. And SimGetTime is an API system layer periodically uses to query the current simulation time, because the simulation time is all managed by the network API, network layer simulator. So this is a snippet of the ASTRA-sim system layer, how these APIs are actually being used. So instead of just being very tightly coupled with a specific network simulator and using a very specific network implementation, as you can see, the system layer is using the common API called SimSend or SimReceive to request a send operation or receive operation simulation. So this is how we decouple the system layer and the network layer. So system layer shouldn't be changed, and as well as need not be changed when we want to use different network modeling behaviors. Whereas this is a snippet of one example implementation of the SimSend, here in this case, the analytical network API implementation. And here, what actually happens to implement the SimSend is real network behaviors, such as calculating the static route, creating the actual chunk, and querying the underlying network simulator to request to send this chunk with this specific route, and so on and so forth. And as you can glimpse from it, the implementation of the network API varies by the network simulation backend, because each and every simulator uses different structure to define a chunk, to define the route, to define the input and output format, and so much more. But because of the decoupling, the ASTRA-sim system layer can stay the same and can support arbitrary network simulator as long as the simulator is able to implement these kind of common APIs defined defined in the document. So by leveraging the common network API, we currently have support for 4 network backends, where the very simple congestion unaware analytical backend and congestion modeling analytical backend, the Garnet backend from Gem 5, and the NS3 for the very much detailed simulation, where these two tastes of analytical backend, which I will cover next, is meant to be very fast first order simulation, where NS3 kind of one is for very complex large parallel internet simulation. The caveat here is that Garnet hasn't been upgraded yet to match the ASTRA-sim 2.0's API, so it's currently working only with ASTRA-sim 1.0 and should be updated. But again, nothing is blocking us to support Garnet. It's not been updated yet to support the new APIs of ASTRA-sim 2.0. That's why it's been obsolete, and with some engineering efforts, we can bring Garnet back when we want to use it. So here's the implementation details of the analytical backend. So in the analytical backend, which is the simplest modeling, here we just leverage an analytical equation to model a send and receive operation. So here we just calculate the link serialization, the link propagation delay by multiplying the number of hops by the link latency, and by adding it with the serialization delay, we calculate the delay happening to send a message from the source to destination. So the SimSend implementation, whenever given, is just to calculate this equation and schedule a event right after this time. So that's why the analytical backend is is able to drive very fast simulation for very large scale systems, but it's not modeling behavior such as congestion modeling or buffer control, buffer management, or other static routing algorithms or dynamic routing. So it's very simple and very fast, and it's very suitable for very large simulations. That's why we come up with another variation of the analytical backend called congestion-aware backend, where we calculate the static route to send the message and we break it down into bunch of different send and receive happening from the passage of each route. Each send and receive is still be model is thing is will still be modeled using the analytical equation, but the different send and receive is now being queued per each queue whenever we have to send more messages over a same link. So that's why it can still enable fast simulation, but still but by this mechanism, we still be able to have a first order congestion modeling. The Garnet backend, as I mentioned, with the caveat of that is currently only working with ASTRA-sim 1.0 and should be updated, leverages the Garnet network simulator from the Gem 5 simulator and is very much appropriate for on-chip and scale-up networks because Garnet brings us more capabilities and more complex network simulations, such as message packetization, verdict-based flow control mechanism, congestion modeling, and so much more. But the downside is that because we get more accuracy, we have to sacrifice the simulation speed. Garnet's much slower than the very simple analytical backend, so may not be suitable for very large scale systems and models. Same goes with the NS3 backend, where NS3 is meant to be more complex inter-networking communication, where we model systems with top-of-the-rack switch, some Ethernet switch. NS3 can actually model the Ethernet protocols, the very complex dynamic congestion control modeling, but because it has to simulate all these, the trade-off is that NS3 simulation is much, much slower compared to the Garnet or analytical network backend. So as you can see here, that NS3 supports very detailed input format where you can even designate some buffer size of a switch, QCN protocol, so much more. But again, the trade-off is that to simulate all these in more detail, the trade-off is that the simulation time takes much longer. So this was the deeper dive into the network layer. But yeah, I wanted to mention that all these different modeling and plug and play manner of different network simulator was possible because we have a common API called network API. And by by sticking to the common network API and making the network simulators conform to the network API, that's how we were able to easily plug in the different network simulators and support different granularities of simulation speed and accuracy. And we expect the very same to happen with the Compute API, which I gave a sneak peek, where we have a very common Compute API and the plug and play of different compute simulator, including analytical, roofline, or other existing compute simulations with different trade-offs of simulation speed and simulation accuracy will be very easy. So this concludes the deeper dive of the ASTRA-sim. And now let me go to the actual demo session of using ASTRA-sim and Chakra. And because it's a demo, please excuse me just putting the slides here and showing the terminals here and the outputs here. So the outline of the demo, we have basically three parts. The first demo will be very simple, understanding how the ASTRA-sim is working, installing Chakra and ASTRA-sim 2.0 structure, using the Chakra execution trace generation API to manually implement and generate the Chakra execution trace, and executing the simulation using the ASTRA-sim 2.0. So the prerequisite for this demo is that the ASTRA-sim project for a submodule is using SSH protocol rather than HTTPS. So if you find any authentication issue when cloning any of the repository, please make sure you have created your own local SSH key and added to the GitHub account. And since the updated ASTRA-sim 2.0 and the Chakra requires protobuf dependency, we have provided and strongly recommend using the Docker environment for this demo. And we will provide how to manually install the protobuf without the Docker in the provided link. So with that, let me directly go and start explaining how to clone and then how to clone ASTRA-sim and how to run it. So for the sake of the tutorial, we provide a sandbox Chakra and ASTRA-sim environment, again for a tutorial purposes, but all the scripts I'm using here are explained in slides, it's been uploaded, and the web page is listing out all the slides I use, as well as the sandbox environment is not very much different from the mainstream ASTRA-sim. So if any question, just reach out to us at any single time. So with that, I will clone this tutorial sandbox repository by running the git clone tutorials. And once done, I will go to the hot eye 2024 environment, then run this clone ASTRA-sim script. And now, yeah, here is the editor I'm showing. The clone ASTRA-sim script, as also shown in the box, is nothing but cloning the mainstream ASTRA-sim and checking out to a very specific tag, which is a sandbox environment, and updating the submodules. And while waiting for the cloning to be done, in the demo slides, the boxes mean the this file snippet of a script of a sandbox script I'm using in the demo. So now the ASTRA-sim's cloning and checking out this very specific branch has been ended. Now, as I mentioned, the execution environment, the easiest to follow is launching a Docker execution environment and running it in a Docker container. We already pushed a Docker image to the Docker Hub, which is called ASTRA-sim tutorial HotEye 2024, which I've already pulled to my local machines. I'm not gonna pull this Docker image for now, but you can anyway anytime go ahead and pull this Docker image. And we can start a Docker container with this downloaded Docker image by linking the current directory to the Docker image. So I'll just run this command to start a Docker container with the folder here attached to the Docker container. So now, as you can see, the Docker container is running, and by going to the HotEye 2024 folder, I'm at this execution, I'm at this folder with the Docker execution environment. So now, because I'm at the Docker execution environment with all the prerequisites, including the protobuf is installed, I can just go ahead and run the install Chakra script. But again, if you see the code snippet, install Chakra shell script is nothing but going to a very specific folder and running the pip install dot, which is, and as you can see from the path, that this is going to the Chakra submodule and just installing the Chakra framework. So I'm waiting for the Chakra submodule to be installed. While waiting for the Chakra to be installed, let me just fast forward to the next slide, which is nothing but the next job to do is compile the ASTRA-sim. Again, saying the compile ASTRA-sim script is nothing but cding to the appropriate folder and running the build script, which is in the mainstream ASTRA-sim as well. So now that the Chakra is being installed, let me run the compile ASTRA-sim to start compiling the ASTRA-sim framework with the analytical network backend. And while this compilation is being done again, before waiting this, let me fast forward and move to the next slide, explaining how to create the simple Chakra ET using the provided Chakra ET generation API, which is defined in the ET demo1 generate all reduce.py. This snippet summarizes that the Chakra ET generation API, but let me just fast forward and actually show you the file generate all reduce.py. Here, as you can see in the main script and in the main function, by using the ET generation API, I'm creating a new Chakra node and assigning it a lot of attributes such as the node's ID to be trivial one, the node's name, and the node type for this case, collective communication node. And you can assign each different individual attributes, such as this is not a CPU operation. The communication type is all reduced. The communication size is code size, which I defined as 1 MB, and other attributes such as the involved dimension. And then by running this encode message, you can save by running this encode message API, you can actually dump the defined ET to a file. So you can imagine that representing things in this API, and by running this Python script, you can generate the Chakra ET files. The compilation is taking longer than I expected, but let me, not reading that, fast forward and explain the network setup instead. So this Python script will generate the workload file, which is a synthetic 1 MB overreduce. We need system info file and network setup file as well. So the target network I want to use here is a ring topology with 8 MPUs with 500 nanoseconds link latency and 50 gigabytes per second link bandwidth. And because I'm using analytical backend here, the input script for representing this is very simple. You basically copy and paste the information here. The topology is a ring. The number of MPU you have is 8. You have 50 gigabytes per second link bandwidth and 500 nanosecond link latency. Again, NS3 input file will be much more complex than this, but because it's analytical, this is the only information you need to configure a network topology in an analytical network. Same goes with the system setup. As you can see here, we can define multiple information such as scheduling policy, endpoint delay. But what I want to emphasize here in terms of this micro benchmarking is that this preferred dataset split defines how much chunk per collective you want to have and which all-reduce algorithm you want to simulate. For this case, I'm using the ring collective communication algorithm. So with that, let me wait for the compilation to end. Yes, 100%. I think will be done very soon. Yeah, it's done. So before running the actual demo, I have to run this generate all reduce to run this API and to generate the Chakra ET. So let me fast forward, go to the demo one folder and run this generate all reduce. And here, as you can see, we run this Python script and generated the all reduce scripts, the ET files. And by running this run demo script, you can see that the simulation has been very quickly run. And by the way, this run demo script is nothing but running ASTRA-sim with appropriate workload system and metric configuration. And when the simulation is done, you can see that the simulation took 117.78 microseconds, but because the cycles in ASTRA-sim is nanosecond scale. Demo 1.2 is a little bit more complex scenario where instead of just having one node, you can represent arbitrary number of nodes because the API is very versatile and flexible. So here, I actually created 3 nodes and assigned the dependency. So here, node 2 with some different characteristic is depending on node 1 and same for node 3. Node 3 is a compute node with 50 microseconds duration and it also depends on node 1. So as you can imagine, by running the generate 3 nodes, another Python script, you can generate the new Chakra ET. And we also the Chakra also comes with a visualization script, so which I add as visualize 3 nodes.sh. But again, if you go to the visualization script, it's nothing but you can see that it's running Chakra's ET visualizer with appropriate input and output file names. And when you see the visualized, the generated visualization result, it's a 3 node as we expected because the blank one means metadata, and as you can see, the actual workload is generated as we expected. 2 nodes depending on the node 1. And by running the simulation, you can see that the simulation runs that this to run this end-to-end workload, it took around 405.5 microseconds. This concludes the demo 1, and I'll quickly go to the demo 2, which is using ET generation API wrappers. What do I mean by wrapper is that this ET generation API can theoretically represent arbitrary ET node, but it can be very daunting and tedious as well. So a lot of work has been done to semi-automate this generation by creating a wrapper and calling the API semi-automatic manner to simplify your work and generate the end-to-end workload-based Chakra ET. Although there's multiple works in this demo, I'm gonna just talk about this text-to-Chakra wrapper because ASTRA-sim 1.0 has been using this text-based representation, where in the first line you mentioned the parallelization strategy, here in this case tensor parallelism, number of layers, and layer information line by line. So in the demo 2, I've already added this example text input file, and Chakra's text to Chakra converter basically parses this workload text-based file and call the API for you. Whenever required, it will create its own Chakra ET, assign the dependency by its own, so you don't have to do the tedious job of calling the API whenever you need a new node or new dependency. So with that, this script convert.sh will do the conversion for you, call the wrapper, and create a complex Chakra ET. But again, the script is nothing but calling the Chakra's ET converter, the text-based ET converter with some input and output directories. So with that, let me go to demo 2 folder and run this convert. The conversion has been very quickly done, and I also added the visualization script, and when I quickly run it, it will show you that the visualization result. And as you can see here, because it's an end-to-end workload, you can see a bunch of different Chakra nodes has been created. But again, the beauty of using the wrapper, such as the text-based converter, is that you don't have to go and define all the different nodes and dependencies. The automated toolchain will parse the input file for you and call the API appropriately and do it for you. And when I run the demo simulation, which simulates the end-to-end simulation of these, as you can see, it run very quickly. And the simulation result is that the end-to-end simulation of this workload is taken around 195 milliseconds for this case. And another sneak peek is that there has been multiple work, not just the text-based represent the converter. So one tool chain we are actively developing is this synthetic chakra execution trace generator, where the assumption is that we want to generate very complex chakra ET for transformer-based large language models, assuming the 4D parallelism, data, tensor, sequence parallelism, and pipeline parallelism. So by representing all the required information in Excel-based spreadsheet, the automated synthetic ET generator will parse all the required information here and will generate a very complex chakra execution trace for you. This is work in progress and will be released pretty soon. Now that the demo 2, we're using the API wrapper is done, let me dive into another very different area of collecting and creating the chakra trace, which is running the actual real system and to running the end-to-end workload over a real system and collecting the traits. Due to the limitation of accessing the real system, I'm not really giving a hands-on demo, but whenever you have a PyTorch model, it's very simple to dump a trace from the PyTorch model by adding some lines of code such as execution graph observer, and by starting the execution graph the graph observer before running any distributed PyTorch model, you can basically dump the PyTorch trace. PyTorch execution, the graph observer, when run currently, is dumping two distinct ET files. One is the PyTorch ET, where it stores operational information such as the data dependency, control dependency, the shape of each tensor, and so forth, and also kinetotrace, where it stores the timing information. So we have to merge them into one, which is we call PyTorch ET plus. And then having the PyTorch ET plus, which is still a PyTorch trace, we can convert it into the Chakra ET to use it in the Chakra ecosystem and for us, ASTRA-sim. So in the demo 3 folder, we have already collected a very simple PyTorch ET trace and Kineto trace for you. And I'll show you in the hands-on demo how to merge them into the PyTorch ET plus trace. Again, I'm gonna run this merge.sh shell script, but it's nothing but running the Chakra's trace link with the appropriate PyTorch ET and Kineto trace to create the ET plus traits. So let me go ahead and go to the demo 3 and run the merge. It merges the Kineto trace and PyTorch trace GPU by GPU and generates the merged ET plus trace, as you can see here, which is a combined trace with both operational and timing information. And with the ET plus trace, we can convert that into the Chakra execution trace. Again, I will run this convert, but this again, very simple conversion and script where we execute the Chakra's ET converter with by mentioning we want to convert PyTorch trace to a Chakra ET trace. So I'll run the convert script, which runs very simple conversion into the Chakra execution trace. And now that we have this Chakra execution trace in .et file, we can run the simulation. So I'll run the run demo 3 script, which calls the ASTRA-sim with the provided ET files and the simulation for the end-to-end. By the way, forgot to mention the trace we collected is a ResNet 50 with Cypher 10 dataset. The simulation has been run, and the end-to-end simulation result is around 58.7 milliseconds. So this ends the demo session. I covered the compilation of the ASTRA-sim and using the API to generate very simple micro-benchmarking Chakra, as well as using one example API wrapper, which is for us text-based converter, as well as using the link trace merger and trace converter to create Chakra trace from a real system trace. I know because of the time, I had no chance to get any questions. I'll for now pass the pointer to Tushar for closing remarks, then I'm happy to take any questions. So back to you, Tushar.
Thanks, Will. So let me just go ahead and very quickly present the very last piece. I know we've also been tracking some of the questions on Slack and answering them. So just to kind of conclude, I know we're almost at time. So this is kind of the overview that we went through today. And after the deep dive and the demo, which I hope will be very useful for several of the users, I just kind of want to take a step back and just again remind that essentially the whole motivation for this work and this tutorial comes from this large scale distributed ML design space, which we've captured into the workload, the system, the compute, the network, and the memory. There's a lot. Each of these individually is a complex design space in itself, and once you kind of put these all together, this is where the complexity actually becomes extremely large. And given, of course, the value of AI in our lives, many emerging supercomputing systems are being designed specifically for this. So to kind of navigate this, we developed ASTRA-sim, which captures each of these different aspects via APIs, as we mentioned. As William mentioned, kind of Chakra almost is like an API for the workload. We have, APIs to feed in collectives, network API, memory API, compute for the different simulators. And we also gave you a glimpse of some of the ongoing work. There is work we've been doing, especially as part of the Chakra working group, to help create not just real traces, which is, of course, something we're doing, but also create synthetic traces that allow for larger design space exploration. For the system layer, our most recent work, in fact, something that we just presented at Hota yesterday, was an API through which you can feed in your own custom collective algorithm written in a DSC like MSQL. Again, as long as it kind of matches the API, you can use whatever DSL you would like and feed it in. We've also been developing our own collective synthesizers, tacos, which will be presented at Micro later this year, and we're also in the process of getting that end-to-end flow working, where you can synthesize your own collective. You describe a network topology, synthesize the collective for that network topology, and then actually simulate the entire system. And another recent development has been the ability to plug in different compute simulators. ASTRA-sim 1.0 used to have scale sim. In 2.0, for simplicity, we just had rootline. Now we are trying to again enable the capability where, just like the network API, you can plug in your own compute API as well, compute simulators as well. So again, just to mention, this is an exciting open source project. We've been very excited that there's been several companies and companies, startups, and academics who've been contributing to the code base. This is just a list of resources to help you out. Like, this is the website. We have a wiki that we've been trying to maintain quite actively, and in fact, right after this tutorial, we'll go ahead and update it further. We've also been doing a lot of work on validation with real systems. Again, thanks to several folks who've contributed validation data, which has also allowed us to, potentially have some correction factors in ASTRA-sim, depending on the system that you're running on. This is just a link to the ASTRA-sim 2.0 paper. We have a mailing list for users, where if you send a question, we'll try to respond to you, and you can also sign up to be on the mailing list. Again, all of this information is also on the GitHub page and on the ASTRA-sim website. And as you mentioned, I think like a major sister project here is the entire Chakra infrastructure. We just talked about kind of Chakra from the lens of ASTRA-sim and how it feeds in traces to the simulator. But as I mentioned, Chakra is a much broader effort, focusing both on trace collection and also replaying it on current systems. And so again, please feel free to check out these resources as well. And just to again recap, I'm Tushar and this was Will, and we are both at Georgia Tech. And I again want to acknowledge, several contributors from both Georgia Tech, especially in this tutorial. I think, we leveraged material that Jinsen, Jung, and Shanghai provided. Saeed Rashidi, who's now at Meta, was actually the original developer of ASTRA-sim back when he was a student. We've had a lot of active contributions from AMD recently. Again, some of the original contributors of AstroSim are now at NVIDIA, Srinivas Tekyung and Sudarshan. For sticking around. I'm going to stop sharing my screen, and we'd be happy to take more questions. I think, we're almost at time, but we'll maybe go and just read out the questions on Slack, the ones that we haven't addressed yet. I think so far we've actually responded to all the questions there directly.
I think so. There was maybe one that I was curious about, incidentally, but it looks like Will, of course, replied to it. Do you support book sim? Not currently. Yeah, and I just wanted to thank you so much for making my job very easy, fielding all these questions. There's great discussion, great pointers, and questions in the chat. So I highly recommend folks to look at those. And yeah, we have time for more questions if anyone has any. Yeah, and if not, I just wanted to extend my sincerest gratitude to the speakers. That seems like such an incredibly flexible and powerful tool and simulator. I could see why it's getting so much attention. Yeah, and with that, that's the end of the uh, tutorial section of the Hot Interconnects conference. I see folks are dropping off quickly. It's been a long day. We've talked about a lot of very deep and lots of technical subjects. Ended it on a very high note with a great demo and a very interesting tool. All materials should be made available. Recordings, I heard rumor this morning that is September 6th is a target for us, but I think it's likely even sooner. Video recordings and slides will be made available. And I'd encourage folks to just keep an eye on the Hot Interconnects LinkedIn profile for any announcements to that degree. Last chance for questions. I had one. Well, I think you mentioned it on the last slide, but I was curious about verification and validation work, how that's going, and if there's anything briefly you could say about, say, um, are some platforms or simulator components more accurate or more challenging than others?
No, that's a great question, Dave. So first of all, again, thank you so much for this opportunity, and very excited and for that so many people are interested. So in terms of validation, that's a great question, right? From what we've observed, I think so. A lot of what we validated, to be honest, is more, I would say, intra-node. So you have, let's say, a 16 node GPU system, or even I think we've done some validation on the cloud TPUs. We actually find that the accuracy is very high. Apart again, because it's topology where collective no congestion, so as it kind of makes sense as long as what we've modeled in terms of collective scheduling is correct, like things work well. One thing that we haven't validated much, and something that is probably where will be very interesting, is once you get again beyond the nodes, and once you have I don't know, InfiniBand RDMA coming in, Rocky. I think that is one aspect we would certainly like to validate. And the other part, which is, I think, and we've done a lot of validation for just individual collectives, but once it comes to the full workload, I think that's again where, their things might start diverging. I think one of the nice things with the Chakra traces is because they capture the exact runtimes, for different components. I mean, we also kind of see a use case where you really focus on just simulating part of that trace that you're interested in. And for that, you can try to, because this has this plug and play nature, you can try to use your validated, high fidelity simulator as the plugin. So what we have is I mentioned kind of the open source piece, but I know some of the users in different companies, like they have their own validated, let's say, network simulator, and that's the one they use. I mean, because they know, the analytical one will naturally not be as accurate at scale, right? So that's kind of the other part that I wanted to mention.
That makes sense. Yeah. And I look forward to seeing, yeah, I think scale out could be a challenge. And of course, there are a lot of moving parts. Um, verification and validation. Any other questions? I'm not seeing any come in. I have one, but it's, maybe kind of hand wavy and high level. It seemed like it's a very fast, maybe it's just the demo. It seems like a fast tool, but I imagine that maybe that's because we're looking at analytical models versus, yeah, something far more expensive.
Yeah, yes. I think whenever we plug in NS3, that
NS3 will kill you.
becomes much, much slower. Yes.
Sure. Yeah. But I imagine you get away with everything being single threaded. And typically it's very, very
At
fast.
this point,
Yeah.
yes, yes. Yeah, I think we've talked about, I think that would require again, the event queue itself kind of being parallel. Yeah, I think we've talked
Yeah.
about, eventually trying to do parallel simulation, but not gotten to that yet. And again, at least for the analytical model, it seems to be not a challenge. But I think once we get to scales of systems with, yeah, 10,000s of GPUs and a lot of these workload traces, there are practical issues there. I think, the trace, I mean, there are issues also related to the Chakra traces. Like those are quite large as well once you start collecting them from real systems. So you
Ah,
have a 10,000 GPU system, large trace files. I mean, there's a lot of those engineering questions that sometimes have come up in some of our discussions. And those are things we'll have to. In fact, I think Will mention kind of protobuf. We've also had discussions about, protobuf and how that's. I
mm,
mean, it's just a lot of these engineering design decisions which end up affecting things. So, one big file getting fed, or like, for each GPU right now, an individual file is being read as the input.
ah.
Those are all, again, things that we'll have to start dealing with as we model larger systems. Yeah.
Well, I'm excited to see the evolution of the tools, and yeah, thank you very much for sharing. Second last chance for questions. I'm not seeing any, so again, let's give a virtual round of applause to our excellent speakers. Thank you for the talk, and thanks everyone for attending, and we'll see you next year.
Thank you, David. Yeah. Bye, everybody.